This talk informs about a planned secondment on Blackbox operators for dynamic data management frameworks with the subtitle Apache, Calcite, Algebra and Optimizer extension. My name is Josef Spillner from Zurich University of Applied Sciences in Switzerland, and I present this on behalf of the ongoing secondment in the CloudStars mobility network. You may know the context of dynamic data management across system boundaries in hybrid environments such as multi-cloud environments where you have private and public clouds or multiple cloud providers or edge clouds where you transfer data generated on one side to another side for data integration purposes. An important capability in such environments are user-defined functions which describe how to transform or convert the data. They come in several flavors, including generic user-defined functions, user-defined aggregate functions, or user-defined tabular functions. They have a different degree of relationality. How relational are they, or can they be? This is an investigation topic. And could a query optimizer, which is going to improve the user-entered query on a SQL level, be optimized with knowledge of this information, with awareness of how these user-defined functions work? In order to answer these questions, we are performing the secondment. I'm staying at IBM Research Israel from June to September this year. To give you an example of how such a user-defined function may be combined in a serverless context, look at this example with Spark. We are creating a single column table that has a column called random number with just 10 rows, and we have two user-defined functions, one which doubles the values in this column locally and one that calls litops to parallelize the doubling of the function to a large degree. Now the optimizer has no idea about how many parallel instances can be invoked in the native implementation. It would invoke one instance of the function per row, which is not optimal due to high overhead. We may have a user-defined function which is able to import multiple rows or even all rows at the same time, as well as output multiple rows. So user-defined functions can work on a one-to-n, one-to-one, m-to-one level, depending on how they are also implemented and described. So here the question is, how can we exploit the information? How can we also make this information available to the SQL parser? In order to find a suitable SQL parser, we looked at Apache Calcite, which is a dynamic data management framework consisting of a SQL parser, a query optimizer, and further integration components, and it supports the dialects of several existing SQL projects, such as SQL databases, MySQL, Postgres, and so forth, but also Spark specific, BigQuery specific dialects. So it is a very capable framework. It is also used by many projects in the big data domain, especially and streaming data domain, and it is the right point to address this question because the impact would be high. A lot of projects would benefit by improving support for black box operators or non-relational operators, especially also in a serverless context. Here we find several points that could be extended, such as the ability to introduce SQL hints on the query level or on the table level. A lot of the features in Calcite are still experimental. They are not always well documented, and this is what makes it a research ambition to go over those points. So the concrete task, therefore, is to extend Calcite's relational algebra representation. We look into the internal representation consisting of Java classes and Scala classes, and we see the mix of UDFs and non-relational operators along with standard relational operators such as filter, join, table scanning, and so forth. We would like to consider a complex data integration flow that ideally crosses several clouds, and we would like to eventually extend Calcite in a direction so that such a complex flow could be translated, including an optimized logical plan that is able to optimize also non-relational or black box operators. The research questions associated with these tasks are: how can we or should we extend relational algebra to allow mapping of those non-relational or black box operators? How can we arrive at an abstract representation of the data integration flow that may come from several different systems such as ETL, ELT systems? And how can we finally enable Calcite to apply those optimizations, which are based on cost predictions? How costly is each operator, including those non-relational or black box operators? The envisioned outcome is, in the end, a practical extension to the Calcite code base, an improved parser that is able to accommodate and to understand those non-relational operators, along with code documentation, unit tests to make sure it works, a set of data integration flows, including, of course, serverless invocations of data transformation, and some outreach in terms of a blog post and a Calcite community interaction, perhaps a talk to discuss the further development of this contribution. Thank you for listening to this talk, and hopefully we are able to discuss that in detail